Hi, my name is Angel Martinez. I am from ITOP and EPFL, and today I will present our joint work with Michael Villamizar, Olivier Canade, and my advisor Gianmarco Dove on fast and reliable human 3D pose estimation from depth images. You can find our code and models in the project repo shown in the slides. Human 3D pose estimation is an essential part of many applications involving human behavior analysis. Especially human-robot interaction scenarios, 3D human pose estimation gives the robot the means for activity understanding and to evaluate the people interaction and engagement. Nowadays, deep neural networks have become the mainstream method to solve the task. Operational research have emerged focusing on color and depth modalities. These works address the task as a 3D coordinate regression, skeleton fitting, or using voxelized representations of the 3D world. In our HRI setting, depth images is the appealing modality for 3D pose estimation given that they provide direct access to the 3D world and are normally available in robotic platforms. Despite the recent success, efficient multi-person 3D pose estimation remains a challenging task. First, deep neural networks are very data hungry and require large computational resources to deploy in real time. Moreover, 3D pose estimation systems need to span a large range of pose and body profile variations, in addition to address the occlusions arising from person and background interaction, common to multi-person HRI settings. Finally, depth maps might contain missing values due to failures in sensing. In that line, our contributions are as follows. We exploit the information that depth data provides and decouple the task in two main steps, 2D pose estimation and 3D pose regression. We recover from detection failures that arise from sensing failures and occlusions with a simple but effective method using a 3D pose prior for 2D to 3D lifting. We propose a novel efficient residual pose regression neural network architecture that performs from 2D lifted points. Finally, we demonstrate competitive performance in single and multi-person scenarios. Our approach comprises three main building blocks. First, an efficient CNN computes confidence maps to compute 2D pose estimates. These estimates are then lifted to the 3D space using the depth camera parameters, forming rough 3D estimates. Finally, a residual pose neural network records the correct pose from the 3D rough estimates. We follow recent breakthroughs for multi-person 2D pose estimation and employ architectures that predict a cascade of confidence maps of body landmarks and vector fields of body limbs. First, we consider the work by Martinez et al. And employ their efficiency in architectures based on residual and mobile networks. Additionally, we employ the well-known hourglass architecture that predicts confidence maps of body landmarks originally used for single-person pose estimation settings. However, we modify the original architecture to additionally predict vector fields to accouplate it into our multi-person pose setting. Given 2D landmark detections, we lift this using the camera matrix K and their corresponding depth image value set. However, error might arise. For example, a 2D detection might have missing depth values due to the sensing failures. Additionally, as it is common in multi-person HRI scenarios, self and between-person occlusions will naturally result in missing body detections. In our work, we avoid feeding these dummy values to our model, which might bias our regressor estimates. Instead, we follow the next recovery approach. First, we replace missing depth values with the mean depth value of the 2D point vicinity. For the case of missing 2D detections, we rely on a 3D limb pairwise prior, following the skeleton shown in the figure. Considering the tree of limbs and taking the spine limb as the limb root, we consider adjacent limbs to encode their 3D direction and length with a joint Gaussian distribution and learn these parameters from training data. Then, to predict the lifted coordinates of a missing landmark, we consider its associated limb Li, whose other landmark is already lifted, and compute the mean of the conditional Gaussian distribution. In our work, we consider that at least the spine limb and other two torso limbs are previously detected. The lifting step provides the rough 3D pose estimates. Note that these rough estimates lie on the depth surface rather than representing the inner 3D joint. Ideally, If we remove all other sources of error, we can argue that such estimates differ from their inner 3D joint by some coordinate offset. Having said that, we model the 3D pose estimation task as follows. Given a rough 3D pose estimate obtained from the lifting process and its corresponding ground truth, we use a neural network regressor to model the residual as in this equation. Here, the function f is the residual to be learned. Graphically speaking, this residual represents the vector coordinate offset necessary to predict the true 3D pose. Architecturally speaking, we model the residual with a shortcut connection between the rough 3D pose and its ground truth. We design an efficient neural network architecture comprising of an input and output layer, and a series of stacked fully connected layers, each of them followed by a batch norm, ReLU activations, and dropout layers. Each of the inner layers in the stack have skip connections. We set the size of the stack to 3. The architecture works as follows. First, the input layer receives the rough 3D pose estimate as input and outputs a high dimensional representation of it. This representation is processed by the inner stack, keeping fixed the dimensionality of the features. Finally, the output layer maps the high dimensional features to the 3D space and predicts the residual pose. This output is added to the input rough 3D pose to form the final 3D pose prediction. We train our neural network regressor using an L1 norm between the ground truth pose and the predicted pose generated from the residual output of our neural network. In practice, we choose to use the smooth L1 norm since we found it provides better results than L2 and plain L1 norms. We perform experiments on 2 public datasets, namely the ITOP dataset with a single person setting and a subset of a CMU panoptic dataset for the multi-person setting. We evaluate the performance of our models with a broadly used mean average precision in a 10 cm radius. We also use the mean error per joint metrics. We experiment with 3 CNN architectures for 2D pose estimation, namely the mobile pose machines with 4 stages, the residual pose machines with 2 stages, and the hourglass with 2 stages. We pre-train the 2D pose CNNs with a large synthetic dataset and fine-tune on the target data. We train our residual pose regressor for 200 epochs with ADAM. We provide more details of the use data and implementation in our manuscripts. First, we assess the trade-off of accuracy and speed of our approach. For this experiment, we use the ITOP dataset and measure the computational requirements using a single GPU. The plots show the precision and recall of the 2D pose estimation performance for the 3 CNNs used. The table summarizes these results using the F-score. Given that the hourglass network has the best 2D performance, we can say that providing better 2D pose estimates reflects directly in the 2D performance, with higher mean average precision and lower MPGPE. In terms of speed, we remark that all the networks run in real time, with the fastest being the MPN model running at 84 frames per second. The pose regressors runs at 1700 frames per second. Finally, we claim that our approach runs very efficiently in real time in a single GPU. For the next set of experiments, we select the hourglass CNN for obtaining 2D pose estimates. Next, we compare the performance of our approach with the state-of-the-art in the ITOP dataset using the mean average precision at 10 cm radius. Overall, our approach shows very competitive results, obtaining the second best performance. The best performing method is the approach by Moon et al., which processes a voxelized representation of the 3D world using a 3D CNN, and uses an ensemble of 10 models for the final prediction. Contrary to that, our residual pose approach is simpler and more efficient and can run in a single GPU. Moving on, we show the performance per body landmarks for our single and multi-person scenarios using the average precision. Naturally, the ranges of pose profile, multiple scales, and the quality of sensing makes the multi-person setup more challenging than the single-person one, where the person appears in a single scale with mostly single pose profile. We note that the most affected body landmarks are the hands and elbows. Note that these body elements are in constant motion and are the most affected by the self-occlusions, compared to other elements like torso and head. We compare different regression settings of our approach in both single and multi-person scenarios. First, we incorporate the confidence of the 2D detection as part of the inputs to the regressor and set a low confidence value for landmarks recovered by our recovery method. Overall, we note that the performance slightly decreases. Next, we remove the prior recovery component from our pipeline and feed the regressor with dummy values. We note that the performance drops, especially for the multi-person scenario, pointing the importance of recovery from failures. Finally, we experiment with 3D coordinate regression by directly predicting the 3D coordinates of the landmarks and dropping the residual connection. We note also that the performance drops for both scenarios, especially for the multi-person setting, where the scenario conditions are more challenging. We present some visualizations of our approach. Let's recap the main contributions of and conclusions of our work. We have addressed the problem of efficient multi-person 3D pose estimation from the images and proposed a residual pose learning setting to refine the lifted 2D detections. We introduced a pairwise 3D limb prior to recover from 2D detection failures and analyzed its contributions in a regression pipeline. Despite the simplicity of our approach, we obtained competitive results in two public datasets with single and multi-person scenarios. Finally, we argue that our method proposes a more efficient alternative for 2D pose estimations in multi-party settings. Thank you very much for your attention.